And we're live. All right. So we discussed before about how to distinguish between critical versus extreme points. Recall a local or relative extremum, which means minimum or maximum, is a point on a graph where a function achieves the smallest or largest value. And then the weird part of it, nearby. Again, it's this last word that brings in the local or the relative. An example we've looked at in the past is the function f of x equals x cubed minus x. And we've agreed that this point has the field what we want to call a maximum. But there are points that are much, much higher. But nearby that value, it's the biggest thing there is. We also agreed that this point should be called a minimum. But again, there are points that are much, much lower. But nearby this point, it's the smallest thing possible. In a later discussion and talk in section, we'll see there's a different idea of a global extreme value, which means that you had the biggest thing anywhere. We're not talking about that here. Question? There is no global extrema of this function. Okay? Other questions? So, oops. Let me leave my green down here. These are what we're going to call extreme points. We argued in class before that if f of x has an extreme point at x equals a, then one of two things must be true. F prime of a equals 0, or f prime of a does not exist. And if a is in the domain of f, this is the definition of a critical point. So one part that I may have left out in a previous discussion is that we only consider critical points if they're actually in the domain. If it's not in the domain, the derivative can't exist. We wouldn't consider it critical because it's not even really there. So the moral we have on the board right now is that extreme point implies that we must have a critical point. And that's where we kind of left things off. Extreme definitely means critical, but we also discussed that the other case may not be true. We gave examples of critical points which were not extreme. The quick examples of those would be examples like f of x equals x cubed, where we saw this last time, it is critical at the origin. And there's also ones like x, if you're less than 0, and something like 3x greater than 0, where we have a bend in the graph. The derivative does not exist at the origin, but it's not critical either. So not all critical points are extreme, but all extreme points are critical. So our task is to figure out when critical points actually are extreme points. And we'll do this via one of two major tools. The first test we'll discuss is called the first derivative test. We'll use the first derivative to decide whether a critical point is a critical point or not. If f of x has a critical point at x equals a, and f prime of x changes sign at x equals a, then x equals a is an extreme point. Now, thus far, I haven't told you whether it's a maximum or a minimum. So at the value a, the derivative is either 0 or doesn't exist. We don't look at what happens at a right now. If over here f prime of x is less than 0, then at a it will switch so that after it it's greater than 0. This tells me the function is going in which direction? Increasing or decreasing? Decreasing. This would mean going downhill. Afterwards, the function is what? It's increasing, and this is a what? This is case 1. Case 2 is the exact opposite. If f prime of x is greater than 0 before a and less than 0 after a, before a, the function was increasing. After a, the function is decreasing. And this would be a maximum. So you can word the first derivative test to have this information encoded in it. I think it's much easier to simply say that if it changes sign, it's an extreme point. Make a quick sketch to see which one it is. Also, when I make statements like this, I am not saying this is true for all values less than a. We're only talking about things nearby. So if this was an example like a equals 4, I'm looking at 3.9 and 4.1, as long as those are close enough that there's no other critical points in between that region. Okay? Good. Do I have enough room? Yes, I do. Test number 2. The second derivative test. If f prime of a equals 0, then there are 3 things we learn. 1, if f double prime of a is greater than 0, then f achieves a local slash relative minimum at x equals a. Case 2, if f double prime of a is less than 0, then f achieves a local slash relative maximum at x equals a. So I've given you the cases when it's greater than 0 and less than 0. We can include a case 3, which is kind of awkward. So I kind of put it off in the bubble. If f double prime of a equals 0, the test fails and no knowledge is gained. What this means must be made clear. This means that it might be a minimum, it might be a maximum, it might be a weird point like we saw on the x cubed graph. But if this happens, you've learned nothing. So we have these two tests here. Obviously the question is, which one should you use? Some quick pro-con discussion. The second derivative test is very user-friendly. It's very easy to memorize. We've seen this picture before, which I sum up as being the second derivative test. The second derivative is positive. You look like this, and you're at a minimum. Second derivative is negative. You look like this, and you're at a maximum. Now, keep the picture in mind. Don't just try to wing it. People say positive, and they think maximum. But again, positive actually means minimum. Negative means maximum. Again, the picture will save the day there. You can think of positive as being happy and uplifting, or a positive emotion, smiling. Negative as being gloomy, therefore downtrodden, therefore you're frowning. Okay, it does kind of match up, at least in the social context. So second derivative test is easy to remember, but it does fail at times. The first derivative test won't fail. However, it does require you to analyze points nearby, which often requires you to do a couple more calculations. So this is often seen as being a little bit more, I don't want to say difficult, but requires more effort. Either one will work in most cases. I will mention the second derivative test does not apply if the derivative doesn't exist. Because if f prime of a doesn't exist, then f double prime of a can't exist either. So if the first derivative fails to exist, you must use the first derivative test. Okay? Let's do an example. And we'll actually use both tests. So a typical type of question will say, find and classify all local or relative extrema of f of x equals x cubed minus x. In different question, let's give you simply a different function here. This is the one we looked at before. We've seen the graph of this since day 1 in this class. Looks something like that. We're trying to find this point, which we expect to be a relative or local maximum, and this point, which we expect to be a local or relative minimum. So step 1, find all critical points. Critical points are always based off the derivative, so the first thing we want to do is find f prime of x. F prime of x for this function, I hope is not difficult, is 3x squared minus 1. F prime of x always exists. So critical point implies f prime of x equals 0. Now this is the step that's often left out. You got to check to see if there's any points where this thing doesn't work. The things will often go wrong if you have a piecewise defined function or if you have a rational expression. And this is the type of wording that kind of becomes commonplace. You get used to doing it. Always exists, so we check for when it equals 0. So this equation, with this here as well, gives me that 3x squared minus 1 equals 0. Is an equation I can use to find all of the critical values of this graph, critical values and all critical points. Solving this out, 3x squared equals 1, or the x squared equals 1/3. X equals plus or minus 1 over root 3, or if you insist on rationalizing, root 3 over 3, which is approximately 0.57. Question? Same thing. This does equal plus or minus the square root of 1/3. So we have two different critical points. Look at the set notation. I have negative root 3 over 3, and I also have positive root 3 over 3. If f is going to have any local or relative extreme points, it must be in this list. So we simply now test it. If x equals negative root 3 over 3, we're going to see what happens. Well, if we look at this, so again, x is approximately negative 0.57, and I make a table, x and f prime of x, for values that are nearby. So, for example, something like negative 0.5. That's a little bit to the left of the right. This is to the right. This is a bigger value than negative 0.57, and also negative 0.6. I'm going to put these into my derivative expression. Negative 0.05 should give me negative 0.25. And negative 0.6 should give me 0.08. So the derivative does indeed appear to change signs. A quick little picture should seal the deal. At root 3 over 3 negative, the derivative is 0. At negative 0.5, the derivative is negative. At negative 0.6, the derivative is positive. So it goes up, is flat, and then goes down. Therefore, the first derivative test says that f achieves a local / relative maximum at x equals negative root 3 over 3.
I'm confused on how you got from square root of 1 over root 3 to root 3 over 3.
The rationalization here? If you multiply both top and bottom by root 3, it's quick, you can do it right just like that. Again, if you're looking at it in decimal form, I'm not a big stickler for having to rationalize the denominator. Some people just freak out if you don't do it. I will mention that doing the other critical point is obviously the value we're looking at right here. Will give you a relative minimum. The details look very, very similar. But I want to compare the first derivative test to the second derivative test. So I guess I should have labeled where step 2 starts. Step 2, test all critical points. Once you've made a list of all critical points, you simply test all of them. Question? No? Check. I'm going to use the second derivative test for that one. So I use the first derivative test to test negative root 3 over 3. I'll use the second derivative test to test if x equals positive root 3 over 3. Recall we had f prime of x equals 3x squared minus 1. What's the second derivative then? Well, a quick calculation gives me 6x. So f double prime of root 3 over 3 equals 6 times root 3 over 3, which I don't care what the value is. All I care if it's greater than 0, less than 0, or equal to 0. This one happens to be greater than 0, which I'll say equals plus sign to give me that little picture of happy face. And therefore, the second derivative test says that f achieves a local / relative minimum at x equals positive root 3 over 3. And the two things you'd want to circle on your paper or those boxes there, with the therefore being optional. But again, it is nice to at least tell me what you've done. I will accept SDT for second derivative test, FDT for first derivative test. As long as you have, a picture or some kind of diagram showing you a sign change for first derivative test, and actually making the calculation for second derivative test here. Again, you can give me a decimal value here from your calculator if you wish to, and then say greater than 0. That's totally fine. Okay?